In 1829, a tiny locomotive called the Rocket changed the world forever, and then we forgot almost everything it taught us. Right now, rusting in museums and forgotten rail yards across the globe, old train engines are holding onto engineering secrets that modern bullet trains and electric locomotives completely abandoned. Secrets about fuel efficiency, mechanical simplicity, and raw survival engineering that would make today's engineers scratch their heads in disbelief. These aren't just relics. These are blueprints we threw away too soon. So let's get right into this list, starting with number 10. Number 10, the Fairlie locomotive. Imagine a train engine that has no front and no back. A locomotive that can run full speed in either direction without ever needing to turn around. That's the Fairlie locomotive, patented by Scottish engineer Robert Francis Fairlie in 1864. Here's how it worked. The Fairlie had two separate boilers mounted back-to-back on a single frame, each feeding its own set of driving wheels on swiveling bogies. That meant every single wheel on the locomotive was a driving wheel. There were no idle wheels just along for the ride. Every axle pulled its weight. Why does this matter? Because modern locomotives waste enormous amounts of energy hauling around dead weight. Wheels that don't drive, carriages that don't contribute to traction. The Fairlie eliminated that problem entirely. On narrow-gauge mountain railways in Wales, Mexico, and New Zealand, Fairlie locomotives hauled loads that engines twice their size struggled with, because 100% of their weight sat on powered wheels. The Festiniog Railway in Wales still runs original Fairlie-type locomotives today, and they still outperform expectations on steep gradients. The secret here is total adhesion weight. Modern train designers moved toward longer, heavier trains with dedicated power cars, but the Fairlie proved that a compact engine using all its weight for traction could be brutally effective, especially on difficult terrain. Modern light rail and tramway designers are only now rediscovering articulated bogie designs that Fairlie perfected over 160 years ago. Number 9, the Shay locomotive. If the Fairlie was clever, the Shay was borderline insane. Ephraim Shay was a logger from Michigan who in the 1870s got tired of watching conventional locomotives slip and fail on the crude, steep, and often temporary tracks running through American forests. So he designed his own engine. The Shay locomotive didn't drive its wheels directly from pistons like a normal steam engine. Instead, it used a vertical cylinder arrangement on one side of the boiler that turned a flexible drive shaft running along the right side of the locomotive. That drive shaft connected to every axle through bevel gears, including the axles under the tender. The result was a locomotive that could crawl up grades as steep as 14%. To put that in perspective, most modern freight railways consider a 2% grade extremely challenging. The Shay could handle 7 times that. The secret the Shay held was the concept of geared traction with universal joints. By using flexible drive shafts and geared connections, the Shay could navigate tracks so rough and so curved that a conventional rod-driven locomotive would derail instantly. The Lima Locomotive Works in Ohio built nearly 2,800 Shay locomotives between 1878 and 1945, and some of them are still running on heritage railways today. Modern trains rely on smooth, well-maintained tracks. The Shay thrived on garbage track. That ability to operate reliably on imperfect infrastructure is a secret that modern rail engineering has almost entirely forgotten. In developing countries where track quality is inconsistent, a return to geared locomotive principles could unlock rail access in regions currently considered impossible to serve. Number 8, the Garratt locomotive. Herbert William Garratt was an English engineer working in Australia, who in 1907 patented a locomotive design that would go on to dominate African, Asian, and Australian railways for decades. The Garratt was an articulated locomotive, but unlike anything before it, the boiler was slung between 2 separate engine units, each with its own set of driving wheels, water tanks, and coal bunkers. The boiler itself wasn't attached to any wheels, it just hung in the middle, free from the constraints of the rail below. This design had 3 massive advantages. First, the boiler could be made as large as physically possible because it wasn't limited by the spacing of the wheels beneath it. Second, the 2 engine units could pivot independently, allowing the Garratt to negotiate extremely tight curves while still being enormously powerful. Third, as fuel and water were consumed, the weight distribution stayed balanced because the tanks were on both ends. Beyer, Peacock and Company in Manchester built over 1,000 Garratts, and they became the backbone of railways in southern and eastern Africa. The South African Railways class GL Garratt was one of the most powerful steam locomotives ever built, generating over 78,000 pounds of tractive effort. The secret here is the separation of boiler from running gear. Modern locomotive designers bolt everything into one rigid frame. The Garratt proved that decoupling the power generation from the wheel assemblies creates a machine that is simultaneously more powerful and more agile. This concept of modular locomotive architecture is something that modern distributed power freight trains are only now beginning to rediscover, over a century later. Number 7. The Stirling Single. Patrick Stirling was the locomotive superintendent of the Great Northern Railway in England, and in 1870 he introduced a locomotive that shocked the engineering world. It had a single pair of driving wheels that were 8 feet and 1 inch in diameter. Just one pair. Most locomotive designers at the time were adding more and more driving wheels to increase traction. Stirling went the opposite direction. He argued that a single pair of very large driving wheels would reduce rolling resistance, maintain higher speeds, and deliver smoother power to the rail. He was right. The Stirling Singles became the fastest express locomotives in Britain, regularly hauling passenger trains at speeds over 75 miles per hour, which was extraordinary for the 1870s and 1880s. They ran the London to York route and were famous for their elegance and reliability. The secret they carried was about rotational efficiency. A large diameter wheel covers more ground per revolution, meaning the piston doesn't have to cycle as fast to achieve high speed. This reduces wear on the valve gear, lowers steam consumption per mile, and produces a smoother ride. Modern high-speed trains use small wheels spinning at incredibly high RPMs, which generates heat and requires complex cooling systems. The Stirling approach of using wheel diameter to achieve speed rather than rotational speed is a fundamentally different philosophy, one that traded mechanical complexity for elegant simplicity. Number 6. The Mallet Compound. Anatole Mallet was a Swiss engineer who in the 1870s and 1880s developed the compound expansion locomotive. His idea was straightforward but revolutionary. Instead of exhausting steam after it pushed a piston once, why not use that partially expanded steam again in a second, larger set of cylinders? The Mallet Compound locomotive had 2 sets of cylinders. High-pressure cylinders received fresh steam from the boiler and did the first round of work. The exhaust from those cylinders, still carrying significant energy, was then piped to a second set of much larger low-pressure cylinders mounted on a pivoting front engine unit. Those larger cylinders extracted the remaining energy from the steam before it was finally exhausted. The result was a locomotive that used 15 to 25% less fuel and water than a simple expansion engine of the same power. On long hauls across the American West, this translated into fewer water stops, fewer fuel stops, and significantly lower operating costs. The Baltimore and Ohio Railroad's old mod, built in 1904, was the first successful mallet compound in North America. It proved the concept so decisively that American railroads ordered hundreds of mallets over the following decades. The secret is compound expansion, which is essentially steam recycling. Modern power plants still use multi-stage turbines based on this exact principle, but the locomotive industry abandoned it when diesel took over. As engineers today explore steam technology for sustainable power generation, Mallet's original compound system is being studied again as a model of thermal efficiency that was perfected on rails long before it reached stationary power plants. Number 5. The GWR 280 Heavy Freight. George Jackson Churchward became the chief mechanical engineer of the Great Western Railway in 1902, and he did something that wouldn't become standard practice in manufacturing for another 50 years. He standardized locomotive components. Churchward designed his locomotives so that boilers, cylinders, valve gear, and other major components were interchangeable across different locomotive classes. His 2800 Class 2-80 heavy freight locomotives, introduced in 1903, shared components with his express passenger engines. If a freight engine needed a new cylinder casting, it could use the same part as a passenger engine. This sounds obvious today, but in the early 1900s, every locomotive class used unique parts. Repair workshops had to stock thousands of different components, and a breakdown of one class meant waiting for parts that fit only that specific engine. Churchward's standardization reduced the Great Western Railway's maintenance costs dramatically and increased locomotive availability because parts were always in stock. His design philosophy influenced every major British locomotive engineer who followed him, including Charles Collet and Frederick Hawkesworth. The secret here is modular design philosophy, applied to heavy machinery decades before the concept was formalized in manufacturing theory. Modern trains are designed by committees and built to specifications that often prioritize novelty over interchangeability. Churchward proved that engineering discipline and parts commonality beat custom design almost every time. The modern automotive industry eventually learned this lesson, but the railway industry, ironically, forgot the lesson that one of its own pioneers taught first. Number 4. The Pennsylvania Railroad T1. The Pennsylvania Railroad T1 was a duplex drive locomotive introduced in 1942. It was designed by Raymond Loewy, one of the most famous industrial designers in American history, and engineered by the Pennsylvania Railroad's own mechanical department. The T1 was different from any steam locomotive before it. Instead of one set of large driving cylinders, it had two sets of smaller cylinders, each driving its own group of wheels on a rigid frame. This was the duplex drive concept. The idea was that smaller, lighter reciprocating parts would allow the locomotive to reach higher speeds without the hammering forces that destroyed tracks and running gear at high speed. And reach high speeds it did. The T1 was regularly clocked at over 100 miles per hour in revenue service, and credible reports put its maximum speed well above 120 miles per hour. Some engineers who operated the T1 called it the fastest steam locomotive ever built. But the T1 carried a hidden lesson that went beyond raw speed. The duplex drive reduced the unbalanced forces in the running gear, which meant less damage to tracks, less vibration in the locomotive, and smoother power delivery. Modern high-speed trains use distributed traction motors for exactly the same reason. Spreading the power across more contact points reduces the stress on any single point. The T1 figured this out in the age of steam. The secret it held was the principle of force distribution in high-speed rail, a principle that modern TGV and Shinkansen designers reinvented from scratch because the steam-era knowledge had been lost when diesel took over in the 1950s. Number 3. The Bulleid Leader. Oliver Bulleid was the last chief mechanical engineer of the Southern Railway in England. And in the late 1940s, he built what many consider the most radical steam locomotive ever conceived, the Leader class. The Leader looked nothing like a conventional steam engine. It was fully enclosed, with a cab at each end, so it could run in both directions without turning. The firemen worked in a central compartment. The driving wheels were hidden inside the body. From the outside, it looked like a diesel or electric locomotive. But the truly radical secret was under the casing. Bulleid used sleeve valves instead of conventional piston valves. Sleeve valves, borrowed from aircraft engine technology, used rotating sleeves around the cylinders to control steam admission and exhaust. They offered better steam flow, reduced friction, and eliminated the complex wall sharts or Stevenson valve gear that every other steam locomotive depended on. The Leader had problems. The central firing compartment was unbearably hot, and the sleeve valves leaked oil. Only one prototype ran under its own power, and the project was scrapped after nationalization. But the secrets it carried were genuine. Sleeve valve technology, enclosed weatherproof bodywork, bidirectional operation, and bogies carrying the entire drivetrain were all ideas ahead of their time. Modern diesel hydraulic locomotives use almost exactly the same layout that Bulleid envisioned. He just tried to do it with steam, and the metallurgy of the 1940s wasn't ready. The concept, however, was sound, and the engineering world quietly borrowed from it for decades afterward. Number 2. The LMS Turbomotive. In 1935, the London, Midland, and Scottish Railway took a conventional Princess Royal class locomotive and replaced its cylinders and pistons with a steam turbine. The result was locomotive number 62-2, nicknamed the Turbomotive. Instead of the reciprocating motion of pistons pushing connecting rods, the Turbomotive used a forward turbine and a smaller reverse turbine geared directly to the driving wheels. The forward turbine developed 2,000 horsepower, and the locomotive ran regular express services between London Euston and Liverpool for nearly 17 years. The Turbomotive was quieter, smoother, and more thermally efficient than its piston-driven sisters. The turbine extracted more energy from the steam because it could expand the steam through multiple blade stages, similar to Mallet's Compound principle, but taken even further. The locomotive consumed less coal and water per mile than equivalent conventional engines. The secret the Turbomotive carried was the viability of turbine propulsion for railway use. When it was finally withdrawn in 1952 after turbine blade damage, it was converted back to a conventional locomotive, and the concept was abandoned. But gas turbine locomotives were experimented with for decades afterward by Union Pacific and others, all chasing the same efficiency gains that the turbomotive had already demonstrated. Today, as engineers explore hydrogen-powered turbines and advanced gas turbines for rail, the data from the turbomotive's 17 years of regular service remains one of the most complete real-world datasets on turbine-driven rail traction ever collected. It proved that turbines work on rails. The industry just wasn't ready to commit to the idea. Number 1, the Stevenson Rocket. We started this script by mentioning the rocket, and we end with it because the secrets it holds are the most profound of all. Robert Stephenson's rocket, built in 1829, won the Rainhill trials and became the template for virtually every steam locomotive built over the next 130 years. But the rocket's real genius wasn't just that it worked. It was how efficiently it worked given its simplicity. The rocket introduced the multi-tube boiler. Previous locomotive boilers used a single large flue running through the water. Stephenson replaced that with 25 small copper tubes, dramatically increasing the heating surface area. More surface area meant faster steam generation from less fuel. This principle of maximizing heat exchange surface area is the foundation of every modern heat exchanger, from car radiators to nuclear power plant cooling systems. The rocket also introduced the blast pipe, where exhaust steam was directed up the chimney to create a draft that pulled air through the firebox. This self-regulating system meant that the harder the locomotive worked, the more steam it exhausted, which pulled more air into the fire, which generated more steam. It was an automatic feedback loop, a cybernetic system designed 119 years before Norbert Wiener coined the term cybernetics. The rocket weighed just 4¼ tons and could reach 30 miles per hour while hauling a load several times its own weight. Its power-to-weight ratio was remarkable, and it achieved this with no electronics, no computers, no advanced materials, just iron, copper, water, and fire. The secret the rocket carries is the most important one of all: elegant simplicity. Modern trains are staggeringly complex machines with millions of components, sophisticated software, and maintenance requirements that demand armies of specialists. The rocket showed that brilliant engineering means achieving maximum performance with minimum complexity. Every time a modern rail system breaks down because a software update failed, or a sensor malfunctioned, or a control system glitched, the ghost of the rocket sits in its museum case at the Science Museum in London and whispers the same message it has whispered since 1829. Keep it simple. If you found this fascinating, hit that subscribe button and drop a comment telling us which old engine secret surprised you the most. We'll see you in the next one.